you look up at the night sky, right? And it is just sitting there.
Yeah, the moon.
The moon. And most of the time we just think of it as this quiet, dead, glowing rock.
Just hanging over our heads every night.
Exactly. But what if I told you it isn't just a rock at all? It is actually a pristine, frozen, 4-billion-year-old time capsule.
Oh, it really is the ultimate planetary archive. Because,
Right.
it lacks an atmosphere, plate tectonics, or liquid water to erode its history.
Right, so it doesn't wash away.
Exactly. The surface we see today is largely the exact same surface that existed billions of years ago. Like, on Earth, active geology just constantly recycles the crust.
But the moon doesn't have that recycling mechanism. It just waits.
Yeah, it just sits there holding on to all these foundational secrets of how our entire solar system evolved.
Which is exactly why we're plunging into this deep dive today. We've got this fascinating stack of university lecture slides covering lunar rocks.
And some incredible data from the Lunar Reconnaissance Orbiter, the LRO.
Right, plus a really great historical summary we're using titled The Apollo Chronicles.
There's a lot of ground to cover.
It is. So our mission today is threefold. First, we are going to explore exactly how humans safely made it to that lunar surface.
Because that was definitely not easy.
Not at all. Second, we want to look at what those famous moon rocks actually told us about the universe once we got them back.
The hardcore geology part, yeah.
And third, why this multi-billion-dollar endeavor from half a century ago still directly impacts your daily life today. Okay, let's unpack this, because before we could pick up a single rock, we had to figure out how to bridge 250,000 miles of empty space.
And actually survive the trip.
Right.
It is incredibly tempting to look back at the 1969 moon landing and just view it as this sudden miraculous leap.
Like we just jumped up and went.
Exactly. But getting there required engineering a flawless system of human survival in an entirely alien environment. The ambition was just massive right from the start. A NASA manager named Abe Silverstein actually named the Apollo program after the Greek god of light, music, and the sun.
Because of the chariot, right?
Yeah, the image of Apollo riding his chariot across the sun perfectly matched the grand, almost mythological scale of what they were trying to accomplish.
Which, just as a quick side note, is why the modern successor program is called Artemis.
Right, appropriately named after Apollo's twin sister, the goddess of the moon.
But reaching that scale involved some really terrifying setbacks. I mean, the testing phase was brutal.
It was. Apollo 1, which was originally called AS-204, was meant to be the first crewed test flight.
But they had that awful cabin fire.
Yeah, during a ground test on the launch pad in 1967, a fire broke out and it resulted in the heartbreaking deaths of 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee.
It is just incredibly tragic.
It really forced an absolute reckoning within the agency. I mean, they couldn't move forward until they understood exactly how to protect the human crew in that enclosed, highly oxygenated environment.
So they basically had to tear it down and start over.
Yeah, massive sweeping safety redesigns.
Yeah.
And from there, the progression just had to be agonizingly methodical.
Agonizingly methodical is right. You look at the uncrewed flights, Apollo 4, 5, and 6, they were just launching the massive Saturn V rocket and testing the lunar module in space.
Right, and Apollo 4 specifically tested the command module's heat shield, because hitting Earth's atmosphere at almost 25,000 miles per hour.
You can't simulate that kind of friction in a lab.
You really can't. They just had to launch a spacecraft thousands of miles out just to hurl it back into the atmosphere to see if the heat shield would hold.
And only after proving that could they put humans back in.
Exactly. Apollo 7 stayed in Earth orbit for 11 days to test the life support systems.
And gave us the first live TV broadcasts, right?
Yep. And then came the huge psychological breakthrough of Apollo 8.
Right, with Frank Borman, Jim Lovell, and William Anders, they actually left Earth's orbit entirely.
Traveled into deep space, orbited the moon, read from Genesis on Christmas Eve.
And Anders captured that famous Earthrise photo.
Yeah, they didn't land, but they proved the navigation worked. Then, Apollo 9 tested the lunar module in Earth orbit, and finally, Apollo 10.
The ultimate dress rehearsal. Thomas Stafford, John Young, and Eugene Cernan took the lunar module, which they called Snoopy,
all the way down to just 15 kilometers above the lunar surface.
And then they pulled back. I keep thinking of this like rehearsing a complex stage play. But if you miss a single cue or a prop fails, the curtain doesn't just go down, you float into deep space forever.
It is a terrifying thought.
But I have to ask, why spend so many missions doing literally everything except the one thing you were trying to do?
Well, if we connect this to the bigger picture, You don't test a parachute by jumping out of a plane on day one, right?
Right, fair enough. You pack it, drop it with a dummy.
Exactly. The spacecraft, the navigation, the communications, spacesuits, every single subsystem had to work in perfect concert. By isolating every single variable across those early missions, NASA ensured that by the time Apollo 11 launched, landing was the only unknown variable left to solve.
And once that final rehearsal was over, Neil Armstrong and Buzz Aldrin finally touched down in the Sea of Tranquility.
The survival mechanics were proven.
So the primary scientific goal immediately took over. Fetch the rocks.
Fetch the rocks.
Because rocks are the ultimate chronometers, right?
Exactly. I mean, much of what we know about the thermal and chemical evolution of the moon comes directly from these samples. And the most staggering realization when geologists got those rocks into the labs on Earth was their sheer age.
We are talking about materials that are over 3.9 billion years old.
Yeah, and to figure out exactly how old a rock is, scientists rely on a process called radiometric dating.
They look at specific isotopes.
Right. They use known decay rates of radioactive parent and daughter isotopes, like potassium-40 to argon-40.
Okay, or rubidium-87 to strontium-87.
Exactly. Or uranium-238 decaying into lead-206.
Here's where it gets really interesting. Radiometric dating is basically like finding a sealed hourglass left sitting on the lunar surface.
Oh, I like that analogy.
Right, because we know exactly how fast that process happens, how fast the quote-unquote sand falls. So by measuring the ratio of unstable parent isotopes at the top to stable daughter isotopes at the bottom,
you know exactly when that hourglass was flipped over. You know the exact moment that rock cooled and crystallized.
it's mind-blowing.
What's fascinating here is that this hourglass technique doesn't just give a birth certificate to one isolated rock. It allowed scientists to construct an entire planetary timescale.
By dating rocks from different impact craters.
Yes, and volcanic plains. Geologists created a chronological map divided into specific eras: the pre-Nectarian, Nectarian, Imbrian, Eratosthenian, and Copernican periods.
That blows my mind. Because we can correlate those precisely dated lunar events with the sheer amount of cratering on the surface, we now use that exact same timescale to estimate the ages of surfaces on Mars, Mercury, and other bodies.
We basically used the moon's rocks to calibrate the clock for the entire solar system.
Wow. And we should probably touch on some of the vocabulary from the sources here too, right? Because they mention things like regolith.
Right, the regolith is that powdery soil on the surface.
Created by micrometeorites constantly sandblasting the rock for billions of years.
Exactly, creating these jagged little glass-fused particles called agglutenates that just cling to everything.
And then there's creep.
Ah, creep. It stands for potassium, rare earth elements, and phosphorus.
Oh, KREP. Got it.
And we'll definitely get into anorthosite and breccia, which are crucial rock types. Because armed with this isotopic stopwatch, the subsequent Apollo missions totally transformed.
They weren't just grabbing random dirt anymore.
No, they were targeted expeditions. NASA selected highly diverse landing sites designed to solve massive geological mysteries.
Let's follow that scientific trail, starting with the dark patches of the moon, the Maria, or seas.
Right, before Apollo, nobody truly knew what they were.
Some scientists thought they might have been actual oceans of water in the deep past, right?
Or maybe impossibly deep layers of dangerous quicksand-like dust. But Apollo 11 proved the Maria were actually vast plains of volcanic flood basalt.
Exceptionally high in iron and titanium, dating back about 3.7 billion years.
And they also deployed the early Apollo Science Experiments Package, or ESEP. It included a seismometer.
They wanted to listen for moonquakes.
Exactly, to understand the lunar interior. Once we knew the Sea of Tranquility was volcanic, the question became, are all these dark regions the same age?
Enter Apollo 12, targeting Oceanus Procellarum, the ocean of storms.
This required a pinpoint precision, landing right on a ray of ejecta from the Copernicus crater.
And incredibly, they landed close enough to walk over and retrieve parts from the unmanned Surveyor 3 probe,
Which had just been sitting there for over 2 years.
the first lunar mechanic job. But geologically, they found basalts that were 3.15 to 3.35 billion years old.
Which led to a massive realization. Even the so-called young Maria on the moon are incredibly old compared to almost anything on Earth's surface.
And they found traces of creep, right?
Yes, finding creep was crucial because it represented the last remnants of a global magma ocean that once covered the entire moon.
Oh, and they proved that granite exists on the moon, which is wild since granite on Earth usually needs water and plate tectonics to form.
It was a huge surprise. But with the volcanic plains mapped, the scientific focus shifted from the interior to the moon's violent past. Apollo 14 aimed for the Fra Mauro formation.
This is the mission where Alan Shepard famously hit golf balls on the moon.
Yes, it is.
Yeah.
But scientifically, they were out there using a two-wheeled handcart to collect samples. Their objective was to find deep crustal material that had been violently excavated by the massive Imbrium impact event.
But when they got the samples back, the rocks were mostly 3.9 to 4.0 billion-year-old breccias. Wait, I want to push back on this for a second. They went all the way to the moon looking for deep crustal rock, but they mostly found breccia instead. How is failing to find what you were originally looking for actually considered a massive win for science?
I love this nuance. That is the beauty of the scientific method. In planetary geology, proving a strong assumption wrong is often just as valuable as proving it right.
Because of what a breccia actually is.
Exactly. It's a rock composed of broken, shattered fragments that have been literally flash melted and cemented together by the intense heat and pressure of a meteor impact.
So finding a field of breccia instead of deep crustal rock proved conclusively that the Fra Mauro region is a sprawling ejecta blanket.
Precisely. They didn't find the deep mantle, but they found the exact fingerprint of the explosion. And by dating those fused-together breccia fragments to exactly 3.9 billion years ago, they successfully dated the actual Imbrium impact itself.
They pinned a precise date on one of the most catastrophic events in our solar system.
Yeah, the science was accelerating, but the physical reality of doing that science was hitting a wall. Pulling that handcart through the lunar dust was just exhausting.
Because of that powdery, glass-fused regolith we talked about.
Right. To truly map the complex geology, the later J-class missions needed a serious upgrade. They needed to travel farther, and they needed a trained geological eye.
The mobility problem was solved on Apollo 15 with the introduction of the Lunar Roving Vehicle, the LRV.
The ultimate off-planet road trip.
Right. Astronauts David Scott and James Irwin unpacked this folding dune buggy and drove it nearly 28 kilometers.
Landed near Hadley Rill, right at the base of the towering Apennine Mountains.
And driving along the edge of the rill, they proved it wasn't a crack from a lunar earthquake, but rather a massive, collapsed volcanic lava tube.
The rover expanded their range, but the physical labor of lunar geology was still brutal. Astronaut James Irwin may have actually suffered a mild heart attack while on the surface.
Wait, really?
Yeah. He was physically straining, fighting to twist a 2.5-meter-long core sample tube loose from the highly compacted regolith.
Just fighting the lunar soil in a pressurized suit under 1/6 gravity.
It took an extreme physical toll. But that core sample was vital for understanding solar wind and micrometeorite impacts over millions of years.
So having mapped a lava tube, the next major geological mystery was the bright, mountainous regions, the lunar highlands.
Right. Apollo 16 landed in the Descartes region. Scientists looking through telescopes assumed these tall, mountainous areas simply had to be formed by volcanoes.
But John Young and Charles Duke didn't find volcanic rock. They found impact breccias dating back 3.8 to 4.2 billion years.
This completely flipped the narrative. It proved that these flat highland areas weren't shaped by slow volcanic oozing, but were formed by pooled, multi-ringed basin impact ejecta.
And the material they found was anorthosite, right? The original, earliest crust of the moon that formed as later minerals floated to the top of that ancient magma ocean.
Exactly. All of this diverse geological mapping culminated in Apollo 17, landing in the Taurus-Littrow Valley.
The final mission, featuring the longest stay on the surface.
And it brought along the first and so far only scientist astronaut to walk on the moon, the geologist Jack Schmitt.
Sending an actual geologist paid off immediately.
It really did. Schmitt noticed something completely unexpected out there in the gray dust: bright orange soil.
He discovered volcanic glass beads dating back 3.5 billion years.
Which was undeniable evidence of ancient fire fountaining volcanoes. Apollo 17 brought back an astounding 110.5 kilograms of meticulously selected rock and soil samples.
And looking at that massive haul offers a really stark contrast to what the Soviet Union was accomplishing at the exact same time.
Yes, the Soviet Luna missions. While Apollo was sending humans, the Soviet Union successfully executed 3 unmanned robotic sample return missions: Luna 16, 20, and 24.
They achieved some remarkable firsts, right? Including successfully sampling the far side of the moon.
They did. But the scale of the return was vastly different. Luna 16 brought back just over 100 grams. Luna 20 brought back a mere 50 grams of material.
50 grams from a robotic scoop versus over 100 kilograms of targeted rocks collected by Cernan and Schmitt on Apollo 17. That is a staggering difference.
This raises an important question that space agencies still fiercely debate today. Why risk human lives when machines can go to these dangerous places for a fraction of the cost?
Well, the 50 grams versus 110 kilograms kind of answers it, doesn't it?
It does. The answer, clearly demonstrated by those Apollo excursions, is that humans possess unique, on-the-fly decision-making abilities that rovers simply do not have.
When Jack Schmitt saw that orange soil, his trained geological mind instantly recognized the anomaly.
Right, he understood its volcanic implications and altered his sample collection strategy right there on the spot. A rover programmed to scoop regolith at point A and point B would have likely driven right past it.
Because we aren't just sending cameras, we are sending intuition, we're sending curiosity. So we've discussed the danger of getting there, mechanics, the radiometric dating, and the massive geological mysteries that were solved. But we promised to talk about why this matters to you, the listener, sitting on Earth decades later.
What is the ultimate legacy of this monumental effort?
Right.
The legacy permeates almost every aspect of modern life. The Apollo program is widely considered the greatest technological achievement in human history. NASA had to invent entirely new fields of material science, computing, and engineering to make it happen.
And as of 2015, the program had yielded over 1,800 documented spin-off products.
Spinoffs that we use every single day.
We are talking about the development of cordless power tools. Black & Decker actually refined their battery technology directly from the requirements NASA set for astronauts.
They needed to drill for those core samples without tripping over cables in zero gravity.
Right. The fireproof materials developed after the Apollo 1 tragedy are now used by firefighters worldwide. Heart monitors, advanced solar panels,
The digital imaging technology in the smartphone you might be holding right now.
even the use of liquid methane as fuel. All of that accelerated because we decided to go to the moon.
But beyond the hardware, Apollo created a profound cultural and geopolitical shift. When William Anders snapped the Earthrise photo on Apollo 8, and later when the Apollo 17 crew took the blue marble photograph of the fully illuminated Earth, it changed human consciousness.
For the first time, humanity could see its entire home in a single frame.
Those images depicted the Earth's frailty, its vulnerability, and its extreme isolation amid the vast, dark expanse of space. Those photographs are widely credited with fundamentally sparking the global environmental movement of the 1970s.
We went to the moon to explore the lunar surface, but what we actually discovered was our own planet.
Beautifully said.
And geopolitically, the program served as a massive pressure relief valve during the heights of the Cold War. It culminated in 1975 with the Apollo-Soyuz test project.
You had an American Apollo spacecraft docking with a Soviet Soyuz spacecraft in orbit.
The commanders shaking hands in zero gravity. It symbolized a powerful transition from the bitter rivalry of the space race to an era of international cooperation.
Which eventually paved the way for the International Space Station.
So what does this all mean? It means Apollo wasn't just about bringing cold rocks down to Earth's laboratories. It was about lifting humanity's collective perspective up.
It forced us to think in planetary terms. It changed how we date the age of the solar system scientifically, and it changed how we view our shared borders culturally down below.
And the story isn't over. We mentioned earlier that the upcoming Artemis program aims to establish a sustainable human presence on the lunar surface. So I want to leave you with a final thought to ponder.
Okay.
The 382 kilograms of Apollo moon rocks sitting in NASA's nitrogen-filled vaults right now, they aren't just historical relics gathering dust.
No, they are not.
They're literal treasure maps for the Artemis generation. When humans step back onto the moon in the coming years, they won't be stepping blindly into the unknown like Armstrong and Aldrin had to.
They will be targeting specific water ice deposits in permanently shattered craters.
And rare earth minerals that we know are there, and we know that entirely because of the physical labor, the geological intuition, and the incredible risks taken by the Apollo crews half a century ago.
It's an incredible foundation.
So the next time you look up at the moon tonight, don't just see a rock. Realize that we are standing on the precipice right now, about to open the next chapter of that 4 billion-year-old time capsule.